Hello everyone, we are Team Rainbow Warriors from RMD Engineering College, Kavarapettai. Today we are here to present our solution for the problem statement titled to develop AML based models to predict time varying patterns of the error built up between uploaded and model values of both satellite clock and ephemeris parameters of the navigation satellites. Let's begin with a small story. Imagine this, you have just landed in a new city, it's midnight, the roads are empty and you open your phone to book a cab. The GPS takes a few seconds to locate you and suddenly it places you 2 streets away. The cab goes to the wrong place, you're standing there confused and it's all because of a tiny delay in the satellite data. Now imagine the same problem, you're driving Google Maps or a pilot navigating through the sky using GPS signals or even a ship in the middle of the ocean depending solely on the satellite positioning. Now what if the satellite that's guiding you is off by just a few nanoseconds? Sounds small, right? But in reality, even a nanosecond timing error can cause a position error of several kilometers on the Earth's surface. That's like missing your destination entirely, not because of human error, but because the satellite's internal clock or orbital ephemeris information wasn't accurate enough. These errors come from multiple sources, may it be changes in satellite orbit due to gravitational pulls, temperature fluctuations affecting the atomic clocks, or even solar radiation and atmospheric disturbance. Today, these errors are corrected using traditional mathematical models, but they are static, slow to adapt, and not predictive. This means the corrections are often reactive after the error happens rather than proactive. So the core problem we are addressing is how can we accurately predict and correct GNSS satellite clock and orbit errors before they cause disruption in the navigation or communication system. To solve this challenge, we have designed a unified AI-driven satellite error forecasting system. Our system uses the combined strength of neural ordinary differential equations and temporal fusion transformers with mixture of experts combined with mixture of transformers and a Bayesian interference, all guided by physics-informed neural networks. Let me explain the flowchart so that you may get a clear understanding of how our solution works. So the process starts with the collection of GNSS satellite datasets, specifically from GEO, MEO1 and MEO2 orbits. Each dataset contains key parameters such as X error, Y error, Z error, and satellite clock bias. The data is typically irregularly sampled, so we have done data pre-processing and data cleaning processes. Once we collect it, we resample all the data to 15 minutes interval and ensure all orbits are time aligned. We handle missing values using interpolation and then normalize all features to remove scale differences between orbits. This step ensures the model sees clear, clean, synchronized, and comparable data across all the orbits. Physics-informed data augmentation. Next, we perform physics-preserving data augmentation to ensure robustness. Unlike random noise, our augmentations maintain the frequency spectrum and temporal dynamics of the signal, using methods such as Fourier-based transformation, phase shifting, and domain-inspired perturbations. This helps simulate real-world scenarios like orbit drift or clock instability while keeping the data scientifically meaningful. The data processed using the physics-informed neural network goes directly into the neural ODE modeling. The cleaned and augmented data is then passed to a neural ordinary differential equation model. Unlike traditional neural networks, neural ODE models continuous time dynamics, meaning they understand how errors evolve smoothly over time rather than in discrete jumps. The neural ODE captures the hidden temporal flow of the satellite error evolution, forming the foundation for the forecasting system. Next, the output of the neural ODE goes into the mixture of experts with temporal fusion transformer. The output from the neural ODE passed into the MOE-MOT layer. Each expert in the layer is temporal future transformer, a model designed to handle long-term dependency and multi-horizon forecasting. One expert focuses on geo orbits, one on MEO1 and the other one on MEO2. The gating network dynamically decides which expert's output to prioritize based on the current orbit characteristics. This structure allows the system to adapt dynamically to the changing satellite behavior, like having specialized mini models for each orbit working together intelligently. Finally, the output is passed on to the Bayesian interference layer. This layer don't just predict a single value, it predicts a distribution of all possible outcomes. Why is this important? Because in real-world satellite system, uncertainty matters. The Bayesian layer gives both the mean prediction, the expected error correction, and the uncertainty range, helping mission operators understand how confident the system is in its prediction. This means our model doesn't just say what will happen, it also tells us how sure it is. Finally, the data is given as the output, which is the error predicted across all the horizons. Let me demonstrate how our system works. Yeah. Now that we discussed the workflow and model architecture, let's move on to the implementation and live demonstration part of our project. We have built and tested our models in Google Colab, where we have separated each major module, the physics-informed neural network, the neural ordinary differential equation model, and finally the mixture of experts combined with the temporal fusion transformer. First, it starts with the physics-informed data augmentation, where the data are augmented to a large dataset, which is passed on to the physics-informed neural network. The idea behind this model is to make the learning process physics-aware instead of only minimizing the data loss. The pin also enforces the orbital motion equation and energy conservation loss as part of its loss function. So during training, the model simultaneously learns from the observed satellite error data and the underlying physical equations governing orbital behavior. This ensures that even if the data is noisy or incomplete, the model's predictions remain physically consistent. Later on, this data is passed on to the neural ODE. Unlike traditional neural networks that learns discrete steps, the neural ODE learns the continuous dynamics of how errors evolve over time. It's like teaching the model not just what the errors are, but how they change with every passing second. The neural ODE takes the pin-corrected outputs as its input and models their evolution across the 7-day training window. It learns the underlying time derivatives and meaning it captures smooth real-world trajectories of satellite behavior. After training, it generates temporal embeddings, which acts as a compact summary of how the error evolves over time. So the third collab file handles the mixture of experts training model, where each expert is a temporal fusion transformer. The mixture of experts framework helps the system decide which expert to trust for the given orbit or the error pattern. Each temporal fusion transformer expert focuses on specific orbit regime, GEO, MEO, or MEO2, and learns long-term temporal dependencies within its data. Together, this setup allows the system to capture both short-term variations and long-term orbital patterns. The model uses attention mechanism to understand which features and time setups are most important for each prediction. All the three trained models are then integrated at here. Now let's move to the final collab notebook, our fully integrated pipeline. This notebook combines all three modules, the fin, the neural ODE, and the mixture of experts with temporal fusion transformers, all working together in a seamless workflow. When we execute this file, the system automatically loads the pre-trained pin, processes the neural ODE outputs, and runs the MOE-TFT model for forecasting. Let me run and demonstrate the output. Now let's break this down. The pin demo training done confirms the physics-based correction model completed training successfully. The neural OD outputs collected line indicates that the continuous time emitting from the OD model were generated and saved. The MOE-TFT training approaches 1 to 5 confirms that the mixture of experts model trained for 5 approaches progressively improving its accuracy on the forecasting task. The 8th day prediction shape 96,4 means the model predicted 96 time points for the next day, each representing a 15 minutes cadence, totaling 24 hours of satellite error forecast across 4 parameters. Finally, the saved 8th day prediction CSV shows that all forecasts are imported for further visualization and analysis. This output represents the complete end-to-end functioning of our proposed system from the raw GNSS data through physics-informed correction, temporal evolution modeling, and intelligent multi-expert forecasting, all the way to the final day ahead predictions. Here is the CSV of the total error predicted on the 8th day. There are a total of 96 rows, each with a cadence of 15 minutes interval. That's all about our project. Thank you for listening.